Okay, I think we can get started. Welcome back, everyone. So we're pretty much just on our review session of the last part of the course. Oh, let me pull up the actual announcements. And so what we're going to do is just go back to example 2 in this first document here. I think we'll probably spend all of today, a good amount of class on Thursday on this document. But if we do have extra time, we'll go down to these other review problems. Unless folks have problems they would like to bring to class or questions that we could address, that would always be a great way to do a review. Otherwise, we'll stick to these problems here. That means down below, there's a whole bunch of other review material that you could take a look at. This right here is just the standard sample problems I gave for exams 1, 2, and 3. And it also includes problems from sections chapter 10 all the way through chapter 12. So it's like this really huge document now. This is just the blank lecture notes that are still pretty good problems. And these were the old quizzes. Pretty much what the quizzes were, they were just an old final exam. Our final exam is probably going to be turned into a bunch of quizzes, the ones that work well for quizzes. And so these are definitely good to come back to. See if you can solve them cold. If you can solve all of those 13 quizzes cold, you're in a really good shape for the course, since those were legitimate final exam type questions all along. So our goal is really just to review some more of these kinds of problems. All of them are going to be pretty standard kinds of problems you'd see on a final exam. And I think that's it for my announcements today, except I did put this here as a bit of a guidance on what the final exam is going to look like. Again, it's going to look a lot like your old quizzes, just kind of strung together into one final exam, but there'll be different problems, different scenarios, different numbers, and that kind of stuff. And how I write the exam is I just go to it by a chapter basis. I select one problem, put it together in a document, and that's usually way too long for a final exam. I might have to take off a couple problems here and there. I'm settling around 10 questions altogether for our final exam. So it'll be from 8 to 10 p.m. 10 questions sounds like a lot, but it's going to be written in a way so that those 10 questions, you should be able to get them done in about an hour and a half for the average person, with 30 minutes built into checking your work. So that's where we're at so far. Any questions, folks, about the upcoming final exam or anything otherwise? Yeah.
There's not like any repeats of sections in the questions, right?
No, I'm not looking for repeats. Yeah, I feel like that would almost be like double jeopardy in a certain sense. And the worst thing that could happen is, say, for example, if someone was writing a really nasty final exam, they could go to chapter 5 and just ask a whole bunch of questions from here. But again, I definitely wouldn't do that. Chapter 5 was from a while ago, so we'll try to review one of those questions at least before we're done reviewing for the whole course. But yeah, I'm thinking about just one per chapter. Other questions so far? Look like you almost had a question.
No, it's just a question like the chapter that was 1.2.
Oh, more like all of chapter 1.
Okay.
So one question from the entirety of the chapter. Yeah. And if we work backwards, we did make an agreement that 12.3, this one is really just going to be on the homework. It's still pretty helpful to get through. It helps us see all the other procedures in context. But for chapter 12, I'm going to select something from this here, confidence interval for a mean. We work backwards to chapter 10. I'm pretty much going to make a question from 10.5. Really, everything we did in chapter 10 was just to get to 10.5. So that's the natural place to ask a question. Going backwards, and none of this is getting written down, but it's on the recording if we have to go take another look at it. Chapter 9, definitely just one section we really focused on, 9.3, and there'll just be one question from there. We're going backwards. Chapter 8 was an unusual section. We only covered one section out of chapter 8, and its whole purpose was to introduce a central limit theorem for proportions so we could get ready for confidence intervals. None of the questions there are actually good exam questions. They weren't on exam 3, for example. They won't be on the final exam. It was just kind of a bridge for us. Going backwards, you could probably expect one normal distribution kind of problem, where you'll have to use normal CDF, inverse norm, potentially give a practical interpretation to a computation, and draw those little graphs to organize information going into the calculator. Now, going back to chapter 5, again, I'm only going to look at one question here, but conditional probability is a pretty standard question. So you have to be ready to pull it out to a hypothetical 1000 table, I'm not going to go for something tricky. It'll be kind of a bog standard, typical type of problem, but you might have to ask a conditional probability question. Questions about independence and mutually exclusive could also be potential problems. Then going backwards, chapter 4, there'll probably be one problem where we're doing a regression. So we'll import information to the calculator if necessary, look at the regression model, make predictions, that kind of stuff, look at outliers, and backwards for more. Chapter 3 is kind of an interesting section. Big takeaway of chapter 3 is when we were first putting information to a calculator, we were calculating things like the sample mean, sample standard deviation. And so you could expect to see a problem, say, doing stuff along the lines of describing center and variability for skew distributions. Something like the 5-number summary would be something you would be expected to do. You might have to do next down here. This is probably the better problem to show. A 5-number problem, a box plot, and then giving a description of what you see in the box plot using the context would probably be a standard type of problem coming out of chapter 3 as well. Then scrolling up above, chapter 2 is where it gets a little bit kind of dicey because there's not a whole lot going on here. But what you might see in chapter 2 is maybe a bar chart, maybe a histogram, and just saying information about what you see there. Then getting down to chapter 1, here, chapter 1 is probably a chapter I might not ask a direct question out of. And the problem with chapter 1 is everything we do in chapter 1, we're doing repeatedly over and over again for all of these problems when we're doing inferential statistics. It's stuff like identify the population, identify the sample, make a description from the unknown population characteristic. Those are the main things we did in chapter 1, and we've been doing them a lot in chapters 9, 10, and 12. So I would say chapter 1, there won't be a direct question out of here, but it'll be stuff that we're really doing all along, kind of scattered about in the other sections. So that's roughly my guide. I've had a lot of the problems written so far, but again, I'm going to pare them down so it's altogether about 10 questions on the final, not about exactly 10 questions. Other questions about that so far, folks? Okay, well, at the moment, we're back to this document. Oh, geez, let me highlight that correctly. We're back to this document here, where we're going to practice some more inferential problems. Then we'll go to review some of the other topics we saw throughout the course. Any questions at all, folks, before we get started? Back on example 2. Okay, well, let's run through this example. I have another document here. Let me see if I can size it better. Essentially, what we're doing in this document is we're trying to look for the right procedure to match the problem. Best way to do that is determine if your variable is categorical or numerical. If you use these notes again on example 1, pretty much all it is a way to deconstruct what is the procedure based on your scenario. So if we had categorical data, we'll either use this method for a confidence interval or this method here if it's a hypothesis test. I forgot which one this one was, but looks like we identified categorical data. There's a lot of giveaways on this. There's no sample mean, there's no sample standard deviation, there's no units given in the problem, but we had a way to think of successes, 1, 2, 8, 8, over failure or over a total sample size. And the thing we're testing is a percentage, not an actual mean. So that told us this is the land of categorical data. We set up our hypotheses, and now we're checking conditions. And as we go through here, I might call this document here and there, but I would definitely have this ready to go. Any of this kind of information will be very, very helpful on the real final exam. Okay, so back to this problem. Let's remind ourselves what we were dealing with here. The problem said we surveyed 2,260 adult Americans. 1,288 indicated they would prefer to live in a hot climate rather than a cold climate. Now we were tasked to do this. Suppose you want to determine if there is convincing evidence that a majority of adult Americans prefer a hot climate over a cold climate. We mentioned that's a really dicey way to indicate a hypothesis test problem, but they really are. They're asking for more than 50%. So we went for a greater than sign for the more than, and that's the value to be tested, the 0.50. P is going to be the true proportion of all Americans that prefer warmer climate. And already that looks like it is greater than 50% on the statistic. But now we're going to test if that is considered far enough away from 50% to be significant. All we know is the sample is representative, and now we're going to go for the rest of the conditions. Any questions at the moment, going through the reminder of the context? Okay, now condition checking is kind of tricky as well whenever we're dealing with categorical data, because there are two ways to check conditions. We'll see them both when we go through this document. But let me put here, just as a reminder, for hypothesis tests, and only for hypothesis test for a population proportion P. So if you're testing little p, here's what we need to check next. Expected successes and expected failures when this thing, H naught, P equals 0.50 is true. So hypothesis testing is really odd on the conditions. We're actually not concerned with 1288 as the amount of successes in the sample. We want to know how many successes would we expect before we even collect any data at all. So the conditions failing or succeeding has nothing to do with the original data. It only depends on your sample size and the statement in your null hypothesis. The formulas go n times p naught, and then n times 1 minus p naught. If that null hypothesis is really true, these two formulas will give us expected successes and the expected failures in the sample before we even collect the data. But from here on out, it's a pretty fast computation. For n, put in a sample size of 2260, and we're multiplying that by p at 0.50. It just means we're cutting it in half, so this turns into 1130. Our benchmark for this is that should have been greater than or equal to 10. We definitely exceed it by a lot, but we just want to show how it works. And so on paper, we should have something like 1130 greater than or equal to 10. Then we just do it all over again. This sample size n is the same, 2260. We're taking 1 minus the same value, 0.50. But really, everything here is still the same. This 1 minus 0.50 is still 0.50. So we're taking 2260, dividing it in 2 to get the same value, 1130, which is also greater than or equal to 10. And so we can say, because both of these exceeded 10 at least, the sample size is large enough. And we definitely expected that. That's a pretty huge sample, 2,260 adult Americans. This was an expensive study to actually commission and run through. So we really do have a large enough sample size, but 2260 adult Americans might not have worked, depending on your null hypothesis. If you were testing something other than liking to live in a warmer climate, maybe we're testing something in the medical sciences, prevalence of a rare gene, this could have been a very small probability, like 0.0003, and the conditions might have failed if we're really testing for something that is a very rare event like that. But in this case, we are meeting the condition overwhelmingly. We're going to have highly accurate results. So now we can say we have a representative sample. The sample size is large enough, so overall, the conditions are met. So whatever conclusion we give, we'll know that we can really stand by it, except for this one. This one we might be challenged on, but we didn't commission the study. That would be up to the experts to defend that statement there. Next, we need a standard error. But we have to remind ourselves if we're doing a standard error, there's like 3 different formulas we need to be aware of to match the right situation. First thing to take a look at for our standard error is our data is categorical and the population characteristic is P. So we should be doing SE for standard error of the statistic P hat. Then it gets even more confusing. If you have a null hypothesis right here where P is a 0.50, then this is the standard error that goes like this as a formula. It's P times 1 minus P, then divide by the sample size N. So every time we do a hypothesis test for categorical data, we have P here, and I did forget one little symbol. It's usually written as P naught. Thanks for seeing that. Yeah, that would be really confusing to leave off. We should keep all of our notation completely the same as we go. P naught is just a reminder. It came from the null hypothesis, H sub 0. So now that we have that corrected there, this is going to be the square root of P naught. Again, just look at your null hypothesis value. It'll be 0.50, 1 minus 0.50, or just 0.50 squared if you prefer. Then divide this whole thing by sample size N. Where did that go? It's in a couple spots, but let's get the official thing, 2260. I usually go very to the top when I collect information because I have a habit of sometimes making a miscopy down here. So it's good to go to the original values when you summarized. So back down here, we're just doing another one of these standard error computations, probably like our 30th or our 40th one in this course. For the calculator, hit second power 2, then 0.50. 1 minus 0.50 is just 0.50 again, so we can save a little bit of time just doing that calculation there. Divide by 2260. And this standard error comes out as a 0.0105. Let's double check. Yes, we want 4 decimal places, 0.0105. Now that we have a standard error, we'll use that in the test statistic. Yeah, go ahead. Our PMOT would still be a 0.50, but if it was less than a majority, we would have put in a less than sign right here instead. So that would have affected the alternative hypothesis. Other questions at the moment? Okay, so now that we have a standard error, now it's time for the test statistic. And this is what's going to walk us towards getting our p-value out. I think we usually highlight our test statistic in this way, so I'll try to stick with that color. Usually purple is just saying something really important to make it pop out. And the good strategy we mentioned here is if you're about to calculate a test statistic, even on an exam, you might as well just write down the formula. It really helps. And that's partial credit on its own. You're telling me what the right formula would be. So we'll put in a p hat to start from this formula. Subtract the value to be tested, p naught, and divide all of that by standard error. So this will then turn into, let's see, did we calculate p hat? Yeah, we just wrote it out as a fraction. So let's throw that into the calculator to start. Let me go over here and just to make the notes a little bit more readable, I'll put a value there as well. 1288 divide by 2260. And if folks wanted to, you could just put that right here, that whole big fraction. You have a pretty accurate answer. It just looks kind of ugly in the calculator. That's why we usually just cranked it out and got an approximation. Our test statistic, we want 4 values. So pretending like this is a WebAssign problem, I'll round this one to 5. 0.56991. Okay, so we have a highly accurate value for the sample proportion of successes. So about 57% of people in the sample prefer warmer climates. So down here, go 0.56991. Okay, so that portion's done. Then we'll take and subtract the 0.50 and divide that whole result by the standard error value we just found, which is 0.0105. Okay, so that's the full structure. Back to the calculator, we're going to find that looks like we're quite a few standard deviations away because the standard error was small in this thing, and this is about 7% off. So let's take 0.56991 minus 0.50, and then division by 0.0105 gives us this as a result. Now that's a lot of standard deviations, so we're going to have a highly, highly significant result. We have 6.6581. So looks like highly, highly significant data. Next thing we'll get is our p-value. Any questions so far, folks, to that stage? Yeah, go ahead.
On when we're doing the test with this thing,
Yeah.
is it like wrong to write it out as V in this case?
Oh, geez, that would have been my mistake. That would have been the correct thing to write. Let me put here. Good call. So that would have been a definite Z. Thanks for spotting that. We should have Z equals on this one. And yeah, it's even in the notes. The test statistic should be Z if we're doing a hypothesis test or categorical data. So thanks for spotting that. That's a weird typo to put into the notes. Weird error, I'd say. And it might look harmless, but it really isn't, because if you put a T, then in the calculator, the next tendency is to go to TCDF to get our actual p-value, but that would not have been correct. Putting in Z is a good reminder. We're really doing, oh, I need to blow that up. We're really going up here to normal CDF. So that is definitely a good thing to put in for best practice. Other questions so far? Okay, thanks again for spotting that weird error there. I guess some of the methods are running together in my mind too, now that they're all on the table. So that's a good thing to separate out. Next thing we'll need is our p-value. And this one will be to 4 decimal places. To get the p-value accurately, we need to go back up here. We might as well copy this all down at this point, because we need the type of test we're doing. This one's a right tail test. And let me just copy from here. So since there's a greater than sign right here, the graph of the p-value will look about like this. There's our normal distribution. This one has a mean of 0. Standard deviation, sigma is 1. So 0 is in the center. Next thing to add is this value to the graph. It's pretty far to the right, so I'll just throw it here. That's not even accurate. It'd be like off the page, clear over here. But that's okay. We're just trying to convey the information. We're trying to get all the area to the right, and this value is 6.6581. In our calculators, this is going to be input 1. Input number 2 is 10 power 99. And those are the last 2 inputs. So after that, we'll get our p-value. And because this is a right tail test, not double-tailed, we don't have to double the p-value this time. Once we find it, we'll just keep it. So to get that area there, we'll go p-value will be the probability that our Z test statistic, let me go back to that color, probability that Z is greater than, and notice the greater than here conveys the area to the right. It's all because of the greater than in the alternative hypothesis. So greater than 6.6581. Let's add one more bit to these notes. Here we'll use normal CDF in the calculator. And again, that's why writing Z is so important as opposed to T. I'll leave this error here X'd out just as that reminder. So normal CDF will be option number 2 in the calculator. Lower value is 6.6581. Our upper is 10 power 99. And everything else is already set. Oh, you know, that's probably going to be okay. But in certain problems, 10 1,099 might not actually work. If our mean is large and our standard deviation is really large, the best number you could really put in your calculator is the largest supported integer, since this will work in any scenario. So with all that set up, here's our p-value. It's to e power negative 11. So this is put in 11 zeros here, and then you can read off your answer. Or we could just say that this is equal to, whenever this happens, to 4 decimal places, as silly as it looks, it's 0.0000, because I would have to read out 10 more zeros before I start writing down 13944. So there it is. We have a highly, highly significant test statistic. And in these cases, it almost wouldn't even matter what alpha is. It's unusual for alpha to be smaller than something multiplied by 10 to the power negative 11. And if we're probably doing something for NASA or something along those lines where things have to be very, very rigorously controlled. So let's take this. We have a essentially zeroed out p-value, and in the notes, I usually always write down this statement just to organize what we're about to say next. Since the p-value, which is essentially 0, I'll just write approximately 0, and that 0 is certainly less than 0.05, which is equal to alpha, we will reject H naught in support of the alternative HA. So now we just have to say, what does that really mean to reject something in support of something else? And that's our practical conclusion using the context. Any questions, folks, with the p-value or making the statement here? Okay, once we have that down, we can always kind of visualize it like this. Ignore that statement, and we're just reading out this using ordinary language. But first we want to say that we have found something, and so we usually start by saying the study provides significant statistical evidence that, then go to the parameter, and we're essentially just going to say the true proportion of Americans that prefer warmer climate is greater than 50%. So we're just reading that out verbatim. And you can change out the language there, make it read a little bit better. But when you're learning statistics, it's not a bad idea to just read it out verbatim the way you see it, going left to right. So I'll write this as the population proportion of all Americans that prefer warmer climates is more than 0.50, or you could say 50%. If you went with percentage, we should say percentage here, the population percentage. If you say proportion, you ought to keep it as a proportion, but I'm not super picky about that. So if we did mix up one and put in percentage, that is okay too. Well, that's the full conclusion on that first example here for our review of inferential methods. Any questions, comments, or concerns so far, folks, on getting through this one? Okay, let me paste on the end of the notes here. End of the notes for this problem. This portion right here, these were the main meat and potatoes pretty much of getting through that whole test. But really, it was also identifying that we had categorical data to start. So those were the methods we used. Let's really get big with a screenshot. Now we're going to convert to a brand new randomly generated problem. And these were really randomly sorted. Here's how our example 3 looks like. It says, how much money do people spend on graduation gifts? So that's a interesting topic. In 2016, the National Retail Federation, I didn't know that's real, but it's apparently a real thing, surveyed 2,511 customers. So let's write out our sample size, or consumers, and is 2,511 consumers who reported that they bought one or more graduation gifts in 2016. The sample was selected to be representative of all adult Americans who purchased graduation gifts. At least say for this sample, the mean amount spent per gift was $53.73. Kind of chintzy. No, just kidding. That's not too bad. And the standard deviation was $20. So that's going to be our symbol S when we go to use the formulas. So S equals $20. And that's all well and good. We ran through the information, found 3 different values to indicate. But the most important thing we need to decide on our own is, what kind of data are these? Is it going to be numeric or categorical? It turns out it's not categorical. And the reason for that is, if we have a value that's given as an average or a mean amount, now we're dealing with numerical data. Another giveaway is anything that also has a unit attached, like time, dollars, distances, heights, things like that, that's probably going to be numerical data. And so I would say probably the bigger giveaway is the fact that we saw this right here. If you see mean, standard deviation, those kinds of things, this indicates we now have numeric data. And looking at this a little bit further, looks like we're doing a confidence interval procedure on this. So for numerical data with a confidence interval, we'll go to this section of the notes. Once I scroll a little bit correctly, there we go. So we have a parameter mu that we have to describe. We were given a statistic like X bar. We were also given S that we'll need later. We need S to get the standard error calculated. And this is going to be the format of our procedure right here for the confidence interval. So let's copy this into context. This is a question that really is on the final exam. Not this actual question, but this type of question. And so those are the methods we'll use. Now we just have to run through it. First thing we need is the unknown population characteristic. But if you have, oh, I forgot to write out X bar. If you have X bar in the problem, you're dealing with mu in your population characteristic down below. And the way this one would read out is mu is going to be equal to the true. You can say average. Sometimes average is not bad. It's more understood to the general public than mean. I'll go with mean. It'll be the true mean of, now we have to go backwards. This is what we would have to say for sure. It is a mean, or you'd say average right here. But we have to say average of what exactly? Up here, the statistic was the mean amount spent per gift. So we can say the true mean, let me try again, the true mean amount spent on all graduation gifts. If you left it here, I definitely wouldn't be too picky. I feel like we should be a little bit more specific. The National Retail Federation is not trying to say this kind of average. They were talking about one specific year, 2016. And they probably redo this study every single year to see how does the population actually change. Are people spending more money, less money, and that kind of thing? So let's say in 2016. So we've got a unknown population characteristic, sometimes called parameter. Our whole goal now is to use this procedure to estimate that unknown population characteristic. The sample mean is already an estimator. We are expecting the true but unknown amount to be around $53. But this procedure also tells us what the error will be in the estimation. We get a whole range of plausible values. And so it's far superior than just reporting 1 point in the estimate, the $53. Next, we have to check if the conditions are met. And that's a good thing to do right after you indicate your parameter, because if the conditions aren't met, we should really seriously consider, should we continue with the study or select a different procedure? On the real final exam, I'm not going to give a problem where you'd have that kind of crisis of, do I finish the problem? You'll always be able to finish out your problem on a real final exam. But looking through the problem, it says, we surveyed 2,511 consumers who reported they bought one or more graduation gifts, and the sample was selected to be representative of all adult Americans who purchase gifts. So we can say at least we know we have a representative sample. I'll say pretty much that. The sample is representative. But now, just like when we were dealing with categorical data, we had to know if our sample size is large enough. Same issue here. So there's more to the conditions. Anyone recall what we would have to check if we're dealing with numerical data? Exactly, that's our rule of thumb coming directly out of the central limit theorem. So, let me fix that first. There we go. We can now say, since n is equal to 2,511, which is definitely bigger than or equal to 30, the sample size is large enough. And this problem is really kind of dangerous in a certain sense. If the sample size was, say, 35, well, it does exceed 30, but we might have been concerned. Looking at this, these are purchases, and we were looking at 2,511 purchases. A lot of them could have been just like graduation cards and things like that, nice kind of fluff gifts, around $30 or so. But I bet you in that 2,511 different purchases, some of them are cars, Lamborghinis, or something extravagant that is very, very expensive. These data are almost guaranteed to be extremely skewed. And so it's comforting to know we have a humongous sample size to overcome what is probably a violently skewed data set in this situation. And so the central limit theorem is going to work really well for us in this case. And if we were concerned if it's going to be enough, we would take a look at that sample size again, and there are further things we can do statistically to decide if we can overcome the skew we see in the actual sample data. So if you take more and more statistics, we start to do loads more work here just to see if the conditions are even met. That can turn into its own big problem on its own, aside from just doing the statistics. But here, we're just thinking about it a little bit as an introductory course. So we just make a couple comments and then make an overall assessment. Here, everything looks great, so we can say overall, the conditions are met. That means we're ready to proceed to the next portion of the problem and have confidence in all of our conclusions. Any questions at all, folks, before we go for the mathy part, standard error, and all that great stuff? Okay, so now that we're doing standard error, one thing to take a look at is always recall if you put down that you have numerical data, that means there's a sample mean floating around, and there's a mu floating around. Mu is the unknown, but it's approximately equal to x bar. But what all that's telling us is that our standard error should now look like this. It is the standard error of the statistic we care most about this time, x bar, the sample's mean. Standard error is going to be S, the sample standard deviation. That looks like something else. Let me fix that penmanship. Divide by square root of sample size. And so this one goes really, really fast. We defined S. I think it was like $20. Yes, there it is. The sample's standard deviation is $20 exactly somehow. So 20 goes here. Divide by the square root of the sample size. We wrote it down here again. That's convenient, but let me double check. Okay, 2,511. So we're expecting a pretty small standard error this time, but that's great. It means our estimation in the confidence interval is going to be highly, highly precise now. Let me minimize that thing. So back to the calculator. Let's clear this out. Hit 20, immediately divide, call up the square root, and let's import 2511. So this is our standard error this time. It comes out as point, let's see, 4 decimal places, 0.3991. Now that we have the standard error, well, that's what goes right here in the confidence interval. We're going to need a critical number T star, and we can put everything together from right here. So critical number T star, this is the one portion of that final exam where I'll just give you the critical number. It'll be baked into the problem right here. I'll just say for a 98% confidence interval, or construct a 98% confidence interval, and use this value of T star. It'll just be printed on the exam itself. Again, the only reason for that is TI-83 calculators were allowed in this class, but they cannot calculate that one thing. So let's write down what you would want to put in your calculator if you're doing this as, say, a homework problem in WebAssign. First thing we'd want to probably put in is either confidence is 0.98 or deal with the degrees of freedom. I mean, we really need to do both, but as a first step, I guess confidence is a good one to start with. Degrees of freedom is sample size -1, so that means it's going to be 2511 -1 for 2,510. Next thing we can write is, if confidence is at 0.98, you can pretty much just do this in your calculator. Go second bars, go to inverse T if you have an inverse T function on your calculator, and it wants right away area. We usually draw a picture for that, and we'll still do that, but here's pretty much the punchline to this. The area is always going to be 1 minus confidence divided by 2. So it's 1 minus 0.98 halves, which is going to be a 0.02 halves, which is going to be a 0.01. And if you're not too worried about doing all that kind of stuff, you can just literally type into your calculator 1 minus level of confidence as a decimal is 0.98. Oh, but we have to type it in correctly. When we close that parenthesis, divide by 2, and you can put a whole entire computation right here for your area. Calculator doesn't care. So all that would give us what we want. Degrees of freedom is 2510, and that satisfies everything. So if you're doing these over and over again, that's probably what you're eventually going to start doing. Just put in the information you need and run through it. But when you're learning this stuff, a picture is always nice. It gives you some kind of mental traction to know what you're looking at, which will help you determine what the calculator gives is correct or not if you have some mental intuition, some picture in your mind. So let's draw this again, just because we can, and it certainly does help. Degrees of freedom is 2510. The center here is down at 0. And our confidence level at 0.98 gives us a central area of 0.98. So we have a picture that looks about like this. 0.98 in the middle. We're going for positive T star, but we've mentioned the formula uses both positive and negative T star. I'm not too worried which value you report. I believe WebAssign wants the positive value though. So we have a T star here that's positive. And the way we're going to calculate it is by taking this area, which is a 0.01, and using it there. So just to complete the notes, here is input number 1 for area. And here's input number 2, the degrees of freedom. So on our calculators, here's what we get as our eventual result of all of that stuff. Critical number is 2.3278. So T star equals 2.3278. And that always looks funky. It's definitely negative. What we found is this value, multiplied by -1, and you get the positive value we're looking for all along, 2.3278. Well, any questions at all, folks, on landing on this value here? Okay, again, I think that's probably the most confusing portion of this new confidence interval once we got into chapter 12. But beyond that, here's what we'll do next. The full formula for the confidence interval is going to be now X bar and subtract critical number T star and multiply it by our standard error, SE of X bar. Everything from here on out is pretty much the nice method of plug and chug. We need to plug in our X bar. Up here, X bar was $53.73 to start. So 53.73. Let me just double check that. That'd be a weird thing to make a mistake on. Then add and subtract. Next thing is what we just found, T star, 2.3278. And last, multiply that by the standard error we found. Up here, it's 0.3991. Now we know what to do next. We're just jamming all of that into the calculator carefully. But here's another reminder on a real final exam. This is essentially almost all of the credit right here if you have what's about to go into the calculator on paper. So 53.73. Let's do the minus first. 2.3278. And then that's multiplied by 0.3991. Okay, I think we've got it. So lower limit is, this is money, so 2 decimal places really make sense. $52.80 is the lower end. This is less than the unknown parameter mu that we described earlier. And mu is going to be less than the same quantity, but convert to a plus in the middle. Either use up arrows. Not all calculators actually support that, as weird as it is. So if that doesn't work, hit second and the enter key. Had to think about that for a moment. This pulls in the last entry, so you can scroll and change that negative sign right here to positive. So now we're up to $54.66 upon rounding. And notice how close all these values are. In the confidence interval, this is the dead center. That was our best one number guess of the sample mean. And it could be as low as $52.80, as high as $54.66. That's a pretty precise estimation altogether. And that's only due to the sample size being quite large in this problem. Last thing to do is just to give a practical conclusion to what we see here. Any questions at all, folks, before we finish off this one? Okay, standard thing we always do is look to the top of the problem. I mean, on a real exam, you don't have to scroll, but technology has its limits. You just need this, really. And we can now say, first, don't forget we have to specify our confidence level. So let's begin by saying we are 98% confident. We are 98% confident. Not sure how I keep doing that weird thing. We are 98% confident that, let's convert to describing mu, the thing in the middle, the true mean amount spent on all graduation gifts in 2016 is between technology is really upset today. I'm not sure why. Is between $52.80 and $54.66. So that's our final conclusion to this estimation right here. Well, we did, folks. That's 2 statistical procedures down. Oh, and I was not paying attention to the time. We've got like 3 seconds left. But any questions or comments at the moment? Okay, sorry for running right down to the second there. I wasn't realizing how short we are. These are kind of fun problems in their own way. The more you learn about them, the more interesting they definitely become. Well, have a great night, folks. If you do have questions, I have a few minutes before my next class. I'll be happy to help out. And when we come back on Thursday, looks like we're going to finish off example 4 here and then example 5 as well. Possibly what I might do is skip the one that's not really going to be on the final exam and just describe it so that we can do a chapter 5 problem, since I feel like that's definitely a good one to hit on the review. Well, have a great one, folks, and I'll see you on Thursday. Any questions?